We have slicing, disc, washer. Now I want to consider my next technique for computing the volume, but like disc and washer, the volume of solid revolution. I will refer to this as my cylindrical shell method. So here I go. Consider the graph of this equation. The region below it, between A and B, so take this region and revolve it about, say, the vertical y-axis. If I take a rectangle over an arbitrary ith subinterval, not that I'm drawing in all the subintervals this time, as with trying to compute area in first semester calculus, there's an approximated rectangle over the ith subinterval. If I rotate that about the vertical y-axis, I will generate this cylindrical shell. And if I compute the volume of the cylindrical shell, sum up the volume of those n, excuse me if I said that correctly, sum up the n volumes, then take the limit of the Riemann sum, I will generate a definite integral. But to compute the volume of this one particular shell, where say, for example, here is x of I asterisk, here is a point at this x and y coordinate, then let's go ahead and take that cylindrical shell. And let me imagine it's made out of tin. Excuse me, made out of tin, not tin. And take its 10 snips right up the middle. If I try to split it apart a little bit, I think it's going to look something like this. If I try to flatten it out as much as I can, then take it to my garage, put it on the table, and use a hammer to flatten it out. I think I can transform that cylindrical shell into a nifty little rectangular solid in 3 space. Where? If you want to talk about the individual dimensions, I think this one right here is merely a small change in the x direction. This dimension right here is this. Now this dimension here, though, that turns out to be the circumference of the corresponding circle. Wouldn't that be computed by looking at 2 times pi times the radius? That being the case, the volume of the solid in 3 space is length times width times height. Now, if you take the limit of the Riemann sum and rewrite that limit as a definite integral, then I think your integral is going to look like this. But of course, I could have revolved about, say, the x-axis. Or shall I say in general, 2 times pi times a radius. Oh, I goofed up in my space. Let me say that one more time. I said 2 times pi times a radius times a height times a thickness. Or how about better yet, let's take this one step further. If the region is bounded above by the graph of that equation, but bounded below by the graph of that equation, nothing's going to change with what I did on the other side of the board except for the computation for the height of the cylindrical shell. Because now the height of the cylindrical shell is not just simply this, but this minus this. I will still schematically refer to this as such. That is going to be your technique for computing the volume of the solid revolution using the cylindrical shell technique.